The anatomy of bridge articulation, engineering bearings for structural integrity, load transfer, and movement. Bridges are dynamic structures identifying the forces that associate structural articulation. Number one, thermal expansion or contraction. Number two, concrete shrinkage and creep. Number three, uh, traffic loads or live loads. Four, wind forces. Five, seismic activity. A rigid bridge will tear itself apart. Unaccommodated displacements generate severe destructive stresses in both the superstructure and substructure. The mechanical fulcrum, the interface between superstructure and substructure. Bearings operate entirely on a principle of convergence. They utilize their small physical footprint to channel massive structural forces through a compact, high engineered point, fulfilling two critical mandates: safely transfer vertical and lateral loads to the foundation, accommodate controlled translations and rotations. Defining the path of least resistance, macro-articulation strategies dictate individual bearing specification. Floating articulation and fixed point articulation. Classifying bearing mechanics, the taxonomy of structural bridge bearings. First, the deformation, movement via material flexibility, elastomeric laminated PTFE top plane. Number two, confined or sliding, incompressible materials trapped under pressure pod disc. Three, mechanical, solid metal components dictating strict movement access, rocker in roller bearing. Specialized seismic, energy absorbing and high rotation systems, lead rubber, high damping rubber spherical. Pure sliding metal bearings are restricted by AASHTO to spans under 15 meter unless combined. Elastomeric bearings, deformation and absorption, translating and rotating through controlled shear deformation. Mechanism accommodates movement via shear deformation, resist vertical loads via steel plates, preventing lateral bulging. Variations: plain, low cost, short span, laminated, high longitudinal compression strength, 100 to 1000 kilonewton capacity, PTFE top, bonded polytetrafluoroethylene for sliding. Optimal use: short spans, flyovers, and structures requiring vibration and sound isolation. POT bearings or pod bearing, high capacity confinement, utilizing elastomeric incompressibility for massive structural loads. Mechanism: the elastomer is confined within the steel pod. Under extreme pressure from the piston, it behaves like an incompressible fluid, permitting multi-axis rotation with minimal resistance. Performance limits: scales to massive loads, 500 to 30,000 kilonewton. Optimal use: incremental launching, major highway, railway, continuous spans, heavy steel structures. Mechanical bearings, beam and rocker systems, strict mechanical constraint, and fixed axis rotation. Pin bearing fixed rocker bearing for expansion application, primarily utilized in heavy steel bridge construction, accommodates movement in one direction only. Highly susceptible to corrosion, requires intensive regular maintenance to prevent locking. Mechanical bearings, roller systems, pure longitudinal translation via metallic rolling, single roller bearing, multiple roller bearing. Technical limitations, operate strictly on mechanical rolling, extremely expensive to manufacture, prone to severe deterioration and corrosion. Multi-roller systems require a separate pin bearing assembly to permit rotation. Spherical and curved bearings, precision multi-axis rotations or complex structural geometries. Mechanism, spherical geometry permits massive rotational freedom while maintaining vertical load transfer. Mated with PTFE for lateral sliding. Performance parameters, handles extreme rotation exceeding plus minus 0.03 radians. Capacity 1000 to 12,000 kilonewton. Requires a minimum coexistent vertical load to prevent structural instability. Optimal use cases, large turning angles, wide decks, curved bridges, extreme low temperature environments, minus 30 degrees centigrade. Seismic isolation bearings, protecting against catastrophic forces through energy dissipation. Lead rubber bearing LRB. The central lead plug is plastically to absorb earthquake-generated shear forces. This action dissipates energy and crucially extends the structure's vibration period, preventing severe deformation. High damping rubber, HDR, an alternative mechanism utilizing specially formulated rubber compounds to achieve equivalent seismic isolation without a central metallic. Controlling the articulation path, the role of guide bearings and surface level expansion joints, substructure control, superstructure control. Guide bearings enforce the precise geometric path of thermal expansion below deck. Expansion joints accommodate this precise movement at the road level, preventing local structural cracking at the parts. Bearing specification and selection metrics, synthesizing load capacities and movement conditions. ULS, bearing type, vertical load, translational ability, rotational ability, optimal use, elastomeric, laminated bearing, vertical capacities 100 to 1000 kilonewton, part bearing 500 to 30,000 kilonewton, line rocker 1000 to 10,000 kilonewton, spherical 1000 to 12,000 kilonewton. Translational ability X/Y, elastomeric bearing, yes, and shear, POT, sliding only with PTFE, line rocker, no, spherical, sliding only without PTFE. Rotational ability in X, Y, and Z direction, elastomeric bearing, yes, part bearing, yes, line rocker, no, spherical, extreme. Optimal use case, elastomeric bearing are used for short spans flyovers. Part bearings are used for major steel concrete spans. Line rocker bearing are used for heavy steel rail bridges. Spherical bearings are used for curved windings. Precision installation mechanics, geometry, temperature calibration, and taper plates. Taper plates, three-cambered girders approach at an angle, but bearings must sit perfectly flat. Taper plates resolve these geometric conflicts and attached via tapered tapped holes to minimize horizontal installation forces. Temperature calibration, bearings must be physically offset during installation based on the ambient temperature. Standard T0 is assumed at 10 degrees centigrade, ESPN 1993-2. To ensure the bearing sits in the exact middle of its expansion and contraction range. Designing for replacement. Life cycle inspection and maintenance under Eurocode 3. The mandate BSEN 1993-2 Eurocode 3 requires all structural bearings to be inspectable, maintainable, and ultimately replaceable. The implementation, these substructures must be designed with physical human access galleries and pre-engineered jacking hardpoints. The process to replace a degraded unit, hydraulic jacks lift the entire bridge deck from the hardpoint, relieving the bearing of structural load for safe extraction without compromising the bridge.